Alright, everyone, let's go to the next question. It's not a difficult one. Don't get afraid just by, observing the length of the question, okay? Let me read it and let's see how we can actually solve the question without using the core concepts, okay? Let's solve this question now. A folded protein in a solution at temperature T has two different conformations A and B. So you have a protein, okay, let's say P, all right, and at temperature T, this P has two different conformations A and B. With the free energy difference delta G, which is equals to Gibbs free energy of B conformation minus Gibbs free energy of A conformation less than 0. So with this information, can I say Gibbs free energy of B is less than Gibbs free energy of A? Yes or no? Can I say this Gibbs free energy of B is less than Gibbs free energy of A? All right. Yep. Great. If I draw the energy profile of this conformation pattern, can I say that the energy of B would be less than energy of A? So let's say over here B is present. So we can say over here A would be present, right? All right then. Next is and separated by a single transition state TS barrier. Okay, so there's a transition state between these two conformations, not an intermediate but a transition state. Okay, I can draw the energy profile like this. Yes or no? Can I? Right? It's simple. All I need to do is separate these two conformations with a transition state. Okay, so I can draw a transition state like this. This is TS barrier. All right then. Next is a single amino acid mutation is introduced in the protein which reduces the enthalpy for both state A and B by the same amount but increases the entropy of state B relative to state A. Now, this information is very important and it's not difficult to understand. What is Gibbs free energy equation? Can I say Gibbs free energy equation is delta H minus T delta S, right? Okay. So, what I am doing, I'm writing this equation for both the conformations, okay, for B and for A. So, we can say for B or for A, GA is equals to HA minus TSA, right? And for B, GB is equals to HB minus TSB, right? Temperature is same. They have maintained the temperature, all right. What they said in the first half of the statement that this mutation in the protein reduces the enthalpy for both A and B by the same amount. So there's a reduction in enthalpy, okay? There's a reduction in enthalpy of A and B by the same amount, all right? Next is but increases the entropy of state B relative to A. But state B has increment of entropy relative to A. That means entropy is increased, or we can say state B's entropy has been increased. Okay. What I can understand from this information is if entropy is increased, that means negative part is increasing, and if negative part is increasing, and HB enthalpy is also decreasing, that is, it is getting more negative, and this part is also getting more negative. That means the Gibbs free energy of B is further decreasing, right? Gibbs free energy of B is further decreasing. What about A? If entropy of A is increased, or let's say there is no change, but HA is decreasing, that means there is a decrement, there is a decrease in Gibbs free energy of A as well, but it is relatively small. All right, it is relatively small with compared to B Gibbs free energy. A and B Gibbs free energy is decreasing, but the magnitude of decrease in Gibbs free energy for B conformation is comparatively more than the decrease in Gibbs free energy of A conformation. That is clear. Okay, what I can write over here after the mutation, okay, there's a decrease in A Gibbs free energy, and this decrease in B Gibbs free energy, but the magnitude is more. Okay, so this is the magnitude. There is high decrease in Gibbs free energy. So now this is GA dash after mutation. This is GB dash after mutation, right? And this was GA before mutation and GB before mutation. Clear? Great. Let's see the next point, if they have anything for transition state. Yeah. Additionally, the entropy of the transition state also decreases. Okay. There is no statement for the enthalpy. There's this the statement is only mentioned for the entropy. So if I write down for transition state minus T transition state, there is decrease in the entropy. So if there is decrease in the entropy, that means the negative part is decreasing, and if the negative part is decreasing, GTS actually increases, isn't it? After mutation, GTS increases because the entropy is decreasing, and you know that if entropy increases, the molecule or the system becomes stable, right? So if entropy is decreasing, what we can say that the negative part is actually decreasing, right? So if the negative part is decreasing, there would be overall increase in the Gibbs free energy of transition state after mutation. So if there would be decrease in the energy pattern, so the transition state barrier would jump to a level, right? It would increase to a level. So we can say after mutation, this is going to be the pattern, right? Blue denotes after mutation. Okay, basically blue ink tells you about after mutation, all right, and yellow tells you about before mutation. Am I clear on this point? Great. Now, which of the following statement is true for the equilibrium population ratio Pa by Pb and the transition state rates after mutation is introduced? See, let's talk about the rates first, okay, because it's easy for us to understand about the rates. They have asked the rates after mutation for A to B process and for B to A. If I take from A to B, this is A to B, right? This is A to B process. Blue ink donates after mutation. So can I say the energy, the Gibbs free energy increases, it has increased after mutation. And if the Gibbs free energy increases after mutation, or we can say, the activation barrier, are you getting it? The activation barrier to cross from to cross the conformation from A to B, to change the conformation to A to B, it has basically increased after mutation. So if the activation barrier has increased, so we can definitely say the rate from A to B decreases after mutation, right? It goes well with the reverse process, that is from A to B, because the transition barrier has increased. Okay, there's a jump, there's increase in the transition barrier. So A to B and B to A, both process rate will basically decrease. Okay, so after mutation, K A to B and K B to A will decrease. Okay, so A is incorrect, B is incorrect. We can say with C. Okay, let's stick to C for the time being, and then D, Ka and Kb decreases. Okay, this is also true for the rate process. Okay, so we have basically eliminated two options. Now let's come to the point of C and D. What is the differentiator? The differentiator is Pa by Pb. Okay, and see, this is Pa by Pb increases, in D it basically decreases. All right, what is Pa by Pb? Let's understand this point. What is Pa by Pb? So it is basically nothing but the population ratio, right? The equilibrium population ratio. See, if something is stable, the population of that particular species will definitely increase, right? If let's say we have a molecule and basically it goes into two conformers. If one conformer is stable than the other one, so the population or the existence of the stable conformer will be more than the existence of the unstable conformer. So with the energy barrier, we can understand this point, that if we look to the energy barrier, so energy of your GB conformer, energy of your B conformer is actually less, right? It's actually less. So basically energy is less. GB is actually less than GA, which is very well true with the first statement as well. So if energy is less, the population of B would be more. The population of B would be more at the equilibrium position, right? A to B. So the equilibrium will actually shift to the direction where the stability is more, right? If the equilibrium constant is high, we say stability of B is high. If equilibrium constant, right, basically is less, we say the stability of A is more, okay? So if the energy of B is less, we say the probability or the population of B is more. So PA by PB basically it further decreases after mutation. Why? Because if I compare GA and GA dash, GB and GB dash, these are the values after mutation, right? So this decrease and this decrease, these two magnitudes are not same. We have understood this point in the first half itself that this decrease and this decrease is not same. This decrease is more, right? Because there is increase in the entropy of B, right? And decrease in enthalpy, which are two favorable processes, which has increased the Gibbs free energy of B to a certain more level, right? So we can say this decrease is actually more, which says that after mutation, the population of B will definitely increase. It will definitely jump, right? So we can say PA by PB will decrease after mutation, which goes with point D, which goes with point D. I hope this point is clear and they have mentioned the slide, the way to get to the answer is B is entropically stabilized relative to A, increasing PB relative to A. Transition barrier should go up as both sides states are stabilized relative to T is lowering the rates. I hope I'm clear on this question. It's a see you yourself can just actually go to the conclusion that the question is not like the typical competitive examination questions where you have a formula, you just put down the values and you get to the correct answer. No, it's not the same. Okay, over here you have to apply the concepts, right? So concepts are very important and will only come if you won't study just for the examination point of view. If you will understand, enjoy your studies, and just push yourself a little bit more to understand the basic, the essence of that particular topic. I'll see you in the next question. Till then, just go through all the questions and let me know if you have any queries.